and welcome Math 212 students. We are looking at probability today. We are going to jump right in. A few of the things we're going to look at are probability of equally likely and not equally likely events, fair games, and expected value. This slide has to do with random and haphazard. If it's a random event, it's something that, we can say, well, if I flip a coin, it's either going to be a heads or a tail. Don't really know what it's going to be, but it's going to be one of those. It's not some sort of haphazard or like I have no idea what it's going to do. If we drop a coin from a certain height, we can say when it's going to reach the ground. However, if I flip a coin, I can only tell you, well, it'd either be a heads or a tails, and I don't know which one it's going to be. I can tell you, however, though, that if you flip it a bunch of times, you're going to approach a point where you have just as many heads as you have tails because there's a pattern or a probability associated with it. And it will land on heads about the same amount of times as it lands on tails. So along with our terms, if I were to say that there's a 25% chance of rain tomorrow, that means there's a 1 out of 4 chance. It does not mean that it's necessarily going to happen. When we give a value to a probability, our probabilities will range, let's get our pen out here, between 0% to 100%. And if the event is not going to happen, that value is assigned a 0. To, if I say it will happen, that event is assigned a 1. So probabilities range between 0 to 100%, or their numerical equivalent, 0 to 1. I wouldn't say that the probability of something happening is a 5. That wouldn't necessarily make any sense. Probability of 1 means it's going to happen. So there are different ways that I can represent probability. I can represent them as a percent, fraction, decimal. I could say 1 in 4 chance, which is what we were looking at when we say 25%, because that's 25 out of 100, which reduces down to 1 out of 4. Odds. Odds are something that's a little bit different. Odds wouldn't be necessarily numerically equivalent to these guys necessarily. It would still, if I want to say the odds against it raining are 3 to 1, you would add up that 3 and that 1 and say the total is 4, and the odds against it raining tomorrow are 3/4. I mean, the way you would say it's 3 to 1, but the probability would then be 3/4 that it's not going to rain. That's how I would state that. Outcomes and events. So let's look at these outcomes and events. If I'm looking at a deck of cards, there are 52 cards in a deck, and sometimes you're going to have these cards and dice problems. So let's look at our 52 cards in case you're not familiar with this. There are 52 cards in a standard deck. There are 4 suits. So those 4 suits are diamonds, hearts, spades, which are typically black. Hold on, spades, and my little clubs here. So let me look at my little clubs. All right, now let's change our color. There are in each of these 13 cards. So there are 13 total cards here, and those cards are in each of the diamonds. I have an ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and a 2. And I have one of those for each of those different suits. These are typically referred to as face cards because they have a face on them. The king, queen, and jack have a face on them. So that is a little bit of review on a deck of cards in case you are not quite as familiar with that. So they asked the probability of drawing a queen of spades. I would write that like this: the probability of a queen of spades would be equal to, I say, how many queens of spades are there in the deck? Well, here are the spades right here, and there's one queen out of 52 cards. So there's that one possibility out of 52 different outcomes. Now, then they asked me what's the probability that I just draw any queen. So the probability of a queen would look like this. And there's a queen of diamonds, a queen of hearts, a queen of spades, and a queen of clubs. So there are 4 of those out of 52. Now this reduces down to 1 out of 13. And that is where they get these numbers here. So let's look at what's next. So we are saying that all the different possibilities are called my outcomes or my sample space. So in this subset here, the E, they're saying the different queens that are possible, but I gave the sample space for all of the different 52 cards. And any little subset of this sample space of I gave the total sample space, which was all of the different 52 cards. That would be called, any subset of that would be called an event. So you could say that this is a subset of my 52 cards that I listed out. We're talking about equally likely, meaning that if I draw a card out, it's equally likely that I'll get one card over the other card, and I don't have 2 queen of spades in the deck and 1 of everything else, that sort of thing. Here's something that's not equally likely, so that kind of helps to clarify this. Notice that if I were to spin this, it's most likely that I'm going to get a 1, because the probability of getting a 1 when I spin this little guy is going to be 1/2, because half of the spinner is covered up with a 1. Now the probability of, say, getting a 1 or a 2, I look at how much is covered up, and it looks like 3/4 of that thing is covered up. So the probability of getting a 1 or 2 is 3/4. Now what about the probability of a 1 or a 2 or a 3 or a 4? Well, that's all of it. So I would say that that would be, you could say that if I split it up into sections here like this, what is that? That's 8 of them. That's 8 out of 8, because it could be anywhere in there. So that would be a 1. But what's the probability of, say, me getting a 5? That would be 0. All right. And looks like they did what we've already done. And what they said was the probability of getting a this or a this. Oh, they did probability of an odd. And what you would do is you would just look at the probability of that 1, which is 1/2. Probability of this 3, which is 1/8, and you would add those together, because that would be the probability of getting a 1 or a 3. That would be the way to win on this. We say in probability that ors you add. That's one way to remember this. Probability of impossible events would be 0. And here they are telling me that probabilities are between 0 and 1. All right, let's look at our theoretical and experimental probabilities. In experimental probabilities, I have to collect quite a bit of data. We were looking at theoretical probabilities of flipping coins and spinning a spinner. Experimental probabilities would be like the collection of that data having to do with tires that we looked at in our last section. And if you'll remember those tires, we collected that data and it modeled a standard normal. So when we're looking at theoretical probabilities, that's rolling dice. That would be my flipping a coin. Those are very typical ones that we start out with, pulling marbles out of a bag. When we're first looking at probabilities, we look at those sorts of things first. And here is the slide talking to us about the experimental probability and collecting data with those tires that we looked at before. All right, we're looking at what's the probability that we'll have 2 boys and 2 girls. So what we need to do if we're going to do this, we look at the different outcomes. So we could have a girl, 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 oops, girl, 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 boy. We could have girl, girl, boy, girl, girl, girl. And then we could have boy, boy, girl, girl. No, I've already done that one, so I need to go to here. I need boy, girl, 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 boy, girl, boy, girl, boy, boy, girl, girl, boy, and then boy, boy. Okay, there's a pattern to this. What I do is I make these guys go every other one. I make these guys go in groups of 2, and then I make these guys go in groups of 4. And so all of this could then happen again with a B in the front. So then I'm just going to copy this list over because this is the other situation that could occur. Okay, there are the different ways that this could happen. How you can count that up is you could say that there were 2 possibilities for the first child, 2 possibilities for the second child, 2 possibilities there, and 2 times 2 times 2 times 2 is 16. So there's 16 possible outcomes. That's the way to calculate that, or we can do our list like I just did. How many on this list include 2 boys and 2 girls? Let's see, there's one, there's one, there's one, there's one, there's one, there's one. So it looks like to me there are 6 out of 16, which would be a 3 out of 8. Make sure I'm not missing any here because I want 2 boys, 2 girls. Okay, I think that gets it. If events A and B are mutually exclusive, then the probability of A happening or B happening is just the sum of those probabilities. We did that when we looked at that spinner when we said the probability of a 1 or a 3. We looked at those and we added those up. What's the probability that our couple has at least 1 girl? Probability of at least 1 girl. Now I'm going to go back to my list, but I'm probably not going to go through and count the 1 girl or 2 girl, 3 girl. I'll just say that this is the opposite of no girls. So probability of at least 1 girl is the same thing as saying 1 minus the probability of all boys, because all boys means there wasn't at least 1 girl. So if I go back a couple of slides, there's the only way for that. So that was 1 out of 16. So this would be 1 minus 1 out of 16, which means 15 out of 16 will have at least 1 girl. That is why we're talking about our complementary. Complementary means exactly what I did, which I did 1 minus the chance that it wouldn't happen at all. Let's look at what's happened with Peppermint Patty here. She went in to go take herself a test, and she forgot that she had that test. So she's wanting to know, if I take a true-false quiz with 10 questions, what's the probability that she'll get a 70% or better? Now this can be a pretty tough question. What's the probability, or let's just look at how many different outcomes there are, because I don't really want to make this list of true false. If I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 2 chances there, 2 chances there, 2 chances there, 2 chances there. So how many different outcomes do I have? 2 to the 10th. Now let me tell you what that is. All right, so you can see there's a lot of different possibilities here. In order to get a 70% or better, I could get 7 of them right, or I could get 8 of them right, or I could get 9 of them right, or I could get 10 of them right. Now, and it wouldn't matter if I got the first 7 right, or if I got that one, 3, 4, 5, 6, 7. I could get them in that order as well. So this probability, finding this answer, is not trivial. I will go ahead and let you know that this probability is a binomial distribution, although you're not going to be required to do this. But this probability is 0.17189, which means probability of getting a 70% is about 17%. So not a very good probability that she's going to pass this test if she totally guesses. And this one is much easier. So if we're going to roll 1 dice, what's the probability? If I'm rolling 1 dice, what's the probability that I get, say, a 1 or a 2? Well, there's one way to get a 1, one way to get a 2. So it's 2 out of 6 different ways to roll the dice, so 1/3. But let's pretend we are going to roll 2 dice. If you're going to roll 2 dice, that increases the complexity of this problem, because 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are my different answers that I could get by rolling 2 dice and summing them. Here are the different ways I could get a 2. I could get a 1 and a 1. That's it. I could get a 1 and a 2, or a 2 and a 1. I could get a 1 and a 3, or a 3 and a 1, or a 2 and a 2. Now I'm going to go ahead and list these out. All right, there they are. There are the different ways to roll 2 dice. And if you add them up, you will get that there's a total of 36 ways to roll 2 dice. Now, if I ask you what's the probability of rolling a 7, since you know there are 36 ways to roll 2 dice, you go 1, 2, 3, 4, 5, 6. 6 out of 36, which is 1 out of 6 times. So if you roll 2 dice, 1 out of 6 times you're going to roll a 7. If I say what's the probability that you roll a 4, you would just count them. There are 3 out of 36. So that would be 1 out of 12 times you roll a 4. What's the probability of rolling a 2 or a 12? That's an or, so I just add. There are 2 different ways to do that out of 36. So 1 out of 18 times you will roll a 2 or a 12. Now this problem is one that you will be required to be able to solve. The multiplication principle, we've actually looked at that, but if I look at this with the 2 dice, there's 6 ways to roll the first dice, 6 ways to roll the next dice, and we say that there are 36 ways to roll 2 dice, and you guys looked at that with me. And if you remember the 4 children problem, and I listed out the different ways to have 4 children, 1, 2, 3, 4, and if I say I'm only going to have either a boy or a girl, if that's my premise, then I say there are 2 choices for the first, 2 for the second, 2 for the third, and 2 for the last. And this would be 16 ways. And if you'll remember, in that problem that I solved, I came up with 16 different ways to have those boys and girls with the 4 children. Let's look at some gumballs. Josie's asking her dad wants to buy 2 gumballs. We have 4 white and 2 red gumballs left, and she really likes the red ones. What's the probability that she'll get at least one red gumball? Well, that probability would be a little tougher, but I'm going to work this backwards, and I'm going to say the probability of no red gumballs. Because if I do at least one, that means I have to do the probability of one, and then I have to do the probability of two, because two red ones would also work, and then I would have to add those. But probability of no red gumballs means that I get a white gumball, and then I get another white gumball. So what's going to happen is I'm going to get a white gumball. Well, what's the probability of my first white gumball? Well, that would be 4 out of 6, because there's a total of 6 gumballs in there. Now, my next gumball needs to be another white one, because I've got to get a white one, and then I've got to get another white one. And we're going to say our and probabilities, you will multiply, because and probabilities decrease the chance that something is going to happen. And when you multiply fractions that are less than 1, they get smaller. So here is probability of my first white gumball, and then probability of my second white gumball. I'm already sitting here holding one, so there's only 3 of them left in there, and out of 5. So this is going to reduce, let's see, 3 goes into 6. What? 2 times 2 goes into that. All right, so this is going to be 2 out of 5 for no red gumballs. But I want probability of at least 1 red, and that's going to be 1 minus none. That'd be 1 minus 2 out of 5. So that would be 3 out of 5 chance that you'll get at least 1 red gumball. All right, we just saw an example of dependent probabilities, because I got a white gumball, and then my next white gumball, its probability changed because I'm already sitting here holding a white gumball. 2 events are independent, such as rolling dice. So rolling dice, dependent would be pulling out gumballs. Another dependent would be taking out multiple cards. Oops, let me write that again. Multiple cards out of a deck without replacement is how we would describe that. So if I take out a deck I take a card out of a deck, and then I take another card out of the deck, and I'm sitting here holding 2 cards. That would be dependent events. Independent events would be if I took a card out of the deck, then I put it back in there and I shuffled, and then I took out another card and looked at that. That would be independent. Fair games. This is what this is basically why probability in math was developed to begin with, is just having to do with somebody trying to win at a game. Expected value. This is, what do I expect to win? Oh, insurance companies. How much do I expect to pay out? They really care about that because they don't want to pay out. How you'll calculate expected value is you'll find the probability and you'll multiply it by the payoff. All right, so you go, I don't know what that means. Well, let's do an example. Here they are writing it out. So probability times the payout, probability times the payout if you look at them. And they just listed them in terms because you don't know how many different ways this can happen. So let's look at something. We've got this game, all right? And I want to know if this is a fair game or not. So I need to figure out what is the expected value. So my expected value, well, it costs $2 to play. So if it's a fair game, the expected value should be $2 to be fair. All right, so it looks like this is cut into eighths, I think. So what is it? We receive the dollar amount on the number. Okay, so my expected value. Let's look at the 5 first. The probability of getting a 5 is 1 out of 8. And the dollar amount that I get is that $5. Nice. Plus, let's do this guy. 1/8 times 2 plus, do that guy. 1/8 times 4 plus 1/8 times 2. Let's crunch all those. All right, so here's where we're at, out of 8, and this would be 7, 13 out of 8. Your expected winnings for this, I'll do 13 divided by 8. Your expected winnings are $1.62 or 3 cents. So if it was fair, it'd be $2. Not fair. And that is how you would get the expected value. So this chapter, this section is, if you've never had any probability, this is a rather tough section because it puts a lot on you and it gave you a lot of information all in one section. If you need any extra time on this, be sure and let me know. If you need any help with any of the questions, be sure and send me an email. Send me an email. That's the best way to contact me, and I will do what I can and try to help you with all of that. All right. Y'all have a good evening. Bye now.